Hello, my name is Daniel. I am not a PhD student from the University of Edinburgh. I've worked here at Codeplay actually for the last year or so. Initially I started off work on the SickleDNN team, which is the neural network accelerator library that Codeplay provides based on top of Sickle, which is the programming model that the company evangelizes. Currently I work on some other Sickle stuff, but one of my former colleagues, PhD who's not with us tonight, did some work on implementing Winograd, which is one of the well-known algorithms for optimizing convolutions, which has been used in neural networks such as the one that the previous speaker, I forgot your name, sorry, and a couple of other applications, but let's go through a couple. So convolutional neural networks have been widely used. Many people know of AlphaGo, AlphaZero, various variants. What fewer people may know is that AlphaGo and its variants actually use a convolutional neural network specifically, with the depth of the input actually being the previous 7 moves of the game. We see another example of neural networks being used in massive particle simulations of the universe. I believe the model for this one was called D3M, standing for deep something something. It's got deep in it. That particular network uses UNet, which is also the one for the medical community. I think that was done about 2 years ago now. And that particular network is widely used for semantic or instance segmentation. So we take in a raw image on the left, where we'll be able to individually segment each of the individual bits, such as blood cells, cancer cells, and what have you. And finally, convolutional neural networks can often be seen in stuff like autonomous vehicles, which is of more immediate relevance to this company. We've worked with Renesas, which are interested in automotive chips. So self-driving cars are, as you might expect, quite common in such vehicles. It was around about in 2012. I've noticed that some of the points of this have been well elaborated by the previous speaker, actually, so I'll be brief. But around about 2012, actually, was when AlexNet, a well-known convolutional neural network, came onto the scene and beat the next best competitor by about 10%. So that was a fairly significant improvement in computer vision accuracy at the time. And every single competitor since to the ImageNet challenge has, without fail, been a convolutional neural network. I guess my desire, and kind of like the one before me, I wasn't sure about how technically aware some of the people in this room might be. So I wanted to start off the meat of this presentation, if you will, with a more simple explanation as to what is a neural network. Now this is a very simple problem. This is, in the case of a classifier, the simplest problem that you can have. It's a degenerate problem. You have 2 classes, you have class A and class B, and we see that they are linearly separable. And we know this is true because we can construct a plane, like the one in the middle, that bisects the 2 neatly, and we can instantly say those points to the left, in this case of the plane, are of class A, otherwise class B. Logistic regression is a more complex idea where essentially this plane you can imagine becomes a slight curved plane. So there's a slight degree of non-linearity in the input, and this is the idea for logistic regression. Multi-class classification is the idea that you could take another class, say of green points in the distance, and you could just construct another plane, maybe in logistic regression also of some slight curvature, that also can neatly bisect the points. But the idea, if you will, with this slight curved plane would be that we could essentially fold space in such a fashion that we have this linearly separable problem right here, which is trivial to solve. And a neural network essentially expands on this again. It repeatedly applies nonlinear transforms until you have an easily solvable classification problem, such as this one. And I should note, all neural networks, in a sense, employ this paradigm. This isn't specific to convolutional neural networks or generative adversarial networks. In a sense, every classification problem specifically can be thought of in this way. So in convolutional neural networks, we typically work on data that is high amounts of local structure. You notice that the value of any individual pixel in an image tends to be highly correlated with that of its immediate neighbors, but not necessarily that with neighbors far away. In the case here of these two filters diagrammatically shown, we have a small filter. In convolutional networks, you typically see us describing a 3x3 filter or an 11x11 filter. And what that means is essentially you can think of a sliding window that we're going to slide over the input. I'll have a better visualization of that in a second. But what I wanted to describe here is that a 3x3 simply refers to the spatial dimensions of the filter, and the 11x11, the spatial, a larger filter. And one important thing to note, as you can see the difference in size, more specifically the area of these two, is that in the case of a 3x3, we have 9 parameters. And consequently, in computers, we also have 9 floating point MAD instructions that we'll do at the low level. So the amount of compute and the amount of parameters is determined by the area or the size of these filters. So in the case of a 3x3, we only have 9 free parameters in our model. The 11x11, we have 121. Just an important point to note. So this is the first of, oh, that's removed all the GIFs. That's a real shame. Okay. Anyway, you can see here that the transparent box is of the input. This is, if you can make it out clearly, a 4. If you look at the left, it's clearer what the size is. The 4x4, and then the depth is of 3. So we would say that this is a 4x4x3 input, right? And that would make 48 elements. And here we have a filter, which is diagrammatically shown in yellow. That is a 3x3x3. We see that it has a depth of 3, the same as the input. And that means that if we were to, I really wish the GIF was active round about now, that if the filter was to move along inside the input, we see that it is only moving with respect to the spatial dimensions of the image. So that's why we refer to this as a 2-dimensional convolution, as opposed to 3-dimensional, where the input would have a greater depth than the filter and you could move into the depth of the image. We don't typically do that in convolutional neural networks, certainly not in the majority of applications. I believe some space-related applications have this, but it's not typically common. Certainly not for the majority of modern neural networks today. So this is, again, I wish there was a GIF here. We have here, instead of a single filter, which we might use to detect a single edge, for instance, we might have another filter that we want to detect curves, slight curves, or another differently angled edge. And so we would see that these filters would slide along in the input, and they would create an input, much like that little blue cube at the front. So this would, as you can probably guess with a 3x3, if it moves along in a 4x4 with a stride of 1, you would have 4 outputs. There are 4 unique locations that you can position this filter at inside the image. And then you do that for each of the individual filters. You stack the results on top of each other. And just to be clear, at each point, you're taking the dot product, right? So you have this cube-like filter, this cube-like slice of the input. You do a multiply add with each of the individual elements as they are stacked next to each other. So what you can do then is you can rearrange this in an equivalent fashion to then have this filter be unfurled, essentially, from this 3-dimensional cube-like thing and unfurl it into a single-dimensional vector. And likewise, we can do the same thing with the input, the slice of the filter at that point. We unfurl the input at this particular stage, and we stack them alongside each other. And then, as you can see, it's much easier to visualize this idea of successive element-wise multiplications and accumulate the results, and that's the dot product by definition. And you can imagine doing this for all 3 filters. So, of course, you do this 3 times in this case, or as many filters as you wish to have. I should note, by the way, that the 3 filters and 3 output features, the input depth of the image being 3 and the output being 3 dimensions is completely coincidental in this case. But what we can do with these dot products is that because they are all done independently of each other, we can then stack them back together in a fashion that, whatever fashion we want. And in this case, we saw that we had those 3 filters, so we can stack them on top vertically next to each other. We take these slices of the input, and there would be 4, but the GIF's not working. And we see how we can stack them on top of each other in this way. And what you're visualizing right now is actually the IMTCAL algorithm, which the people of the CAFE Deep Neural Network Library, if any of you have heard of CAFE, misleadingly call the CAFE trick. It's not. It's the intercal trick. This was a simple algorithm, or transform, I should say, that takes an image and turns it into a matrix-like representation like the one seen on the left. And the advantage of this is, now that we've rearranged our data and our filter from initially these cube-like entities, we've now transformed them into nice simple matrices. And that means that I can now make this the problem of sickle blast, which is our linear algebra library, homegrown again in Codeplay. So this would be a very good algorithm. It is a good algorithm for a wide variety of inputs. Matrix multipliers have been well optimized and well studied over the last few decades and have some ridiculous amounts of money and time put into optimizing them within the nth degree. So this would initially appear to be, some would say, like the optimal algorithm, the best way you could possibly do this. It's not, but you would think that initially. And one of the key problems with this particular approach is the memory duplication. So recall that here, if you would imagine, just human memory for a second, that you imagine these three filters sliding along the input, that you would imagine that there is a degree of overlap between the successive filters. So here in the top, in the four corners of the input, you can see up here, 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 and here, that we have these sections that are not overlapping at all. That we have with the yellow sections that there is a degree of overlap between two filters, and the center red hot region, the hot region, is 3, an overlap of, 4 in this case actually. And the problem is that this memory duplication can become quite severe. Recall that I mentioned that this is a 4 by 4 by 3 input. So if you do the maths, 4 times 4 times 3, 48. But conversely, if you look at each of the individual slices of the input unfurled and stacked on top of each other, we actually have 3 times 3 times 3 times 4, or 108 elements. We more than doubled the size of the input in order to have a nice, efficient, single, dense matrix multiply. The additional problem is that this hot region is the one that grows the fastest with respect to the size of an image. So if you imagine more like, this is an easy example, but say you had an image of size 224 by 224 by 3, that region in the center is the one that grows and is the predominant one in that image, and the memory duplication can become quite severe. These 4 points in the corners, they are not duplicated at all, but these yellow regions grow linearly with respect to the height and width of the input respectively, and the red hot region, as I've said, grows quadratically quite quickly. And this can be a problem, particularly at training time, because in neural networks, researchers typically would want to train on a batch of, say, 4, 16, 32 images. And so the duplication is multiplied by that number again. For deep layers, this can become quite a problem, and your memory can be uncomfortably running out quite quickly and early on in training. So you then might wonder what a better algorithm for this might be. Well, some man named Winograd, way back in the 1980s, early 1980 I might add, was able to observe that if you take a filter which up in the top block is represented with G0, G1, and G2, traditionally the way that we represent filters is denoting it with G, and the input is with 2 slices of the input, D0, D1, and D2, D1, D2, D3. If you take a single dot product between 2 vectors, this is provably the minimum number of floating point multiplications that one needs to perform. And we quite often care about this number of floating point multiplications in low-level code, such as that in cyclednn, because that's often a proxy for the amount of overall compute that one must do in the neural network. But it would not necessarily be the case that doing 2 dot products, or rather, more specifically, sliding G0, G1, and G2 with these 2 successive layers of the data matrix on the left, that is the minimum number of multiplications. And in fact, it's not. So if you then were instead to substitute this and not do this in a naive way, but in fact to do this seemingly intractable arithmetic expression, which is then expanded upon in the second block, that this actually can get you, if you take a look, if you look at M1, M4, M2, and M3, the number of multiplications that you actually need to do without dividing or multiplying by a fixed constant, which you can do ahead of time, in this case is 4. Not the naive way of 6. So there is a very small improvement here, but the benefit of this observation is that this not only extends to two-dimensional inputs, but actually we can end up having a very significant saving for much larger inputs. And this is the key idea behind Winograd. So we look at this seemingly random expression that we have here, and we can see that we have a variety of a bit of linear algebra, some simple matrices. And you might wonder where the hell these matrices come from. We'll get to that in a second. But you might also note that they're very simple. We have ones, we have zeros, and we have halves. And this is nice for us because ones just represent substitution, in this case a bit of addition, and zeros mean don't do anything. So that's quite nice. And we see here that we have G and D at the bottom. And AT essentially represents an inverse transform. So if you look at the expression below, we see D, the data, remember, a small little bit of data, is first multiplied, and I say multiplied with inverted quotes because we're not really multiplying, because as we see with B, with all these ones and zeros, we're just adding and subtracting. And then we see that by doing a second multiplication with transpose B, that actually is what allows us to do this in the two-dimensional case. This simple algorithm that I've shown you here can be generalized to 2 dimensions, and the way that we do this is, rather than with a single matrix, we do it twice, and this allows us to do it for the two-dimensional case. If you wanted to do it 3-dimensional, again, you have another B, and you have another G in the inside, and another AT on the outside. But you first transform the input, you transform the filter, and then that center little dot thing that you might wonder what that is, that's technically called the Hadamard product, if I remember correctly. I'm not entirely sure. As I said, I'm not a PhD. But it represents pointwise multiplication. So the only actual multiplies that are done in this single step are encapsulated in that little dot right at the very center of the input. And the result of that entire expression is then inverted by first performing a multiplication, again, quotes, with AT followed by A. And then you have the exact same result as what you would get with the direct approach. If this does not look right to you, I did actually go through the arithmetic. I'm not deriving it myself in front of you because it is frankly far too much and really not something you want to do. I can promise you that with absolute certainty. So in about 2015, when intercall was an algorithm developed in majority of libraries such as TensorFlow, Caffe, Theano, bunch of others, it was a very well-performing algorithm, but it wasn't necessarily scaling well to the larger networks and the considerably greater amount of training that companies like Google and Amazon and Facebook and others were doing at the time. So 2 researchers, both from Nirvana, if I remember correctly, Nirvana Systems, were called Andrew Lavin and Scott Gray. I believe the latter is working at OpenAI. The former is doing some consultancy work, not entirely sure. But in 2015, they developed a paper that used this observation from Shmuel-Winograd's 1980s paper, which was primarily focused on signal processing, and applied it to convnets. So we can see here that we have this little f, m times m, r times r. You might wonder what that means. In this case, with f, 2, and 3, it's actually quite reasonably straightforward. 2 on the left denotes the number of outputs. So we see here that if we have the dot product of G0, G1, and G2, with D0, D1, D2, that's 1, the second trio, the second element. So there are 2 outputs that are done, and we have a filter of size 3, hence the 3 on the right. So f of number of outputs, number of elements in your filter. And that's what that f, m times m, r times r is. This is generalized into the 2-dimensional case. We now compute 2 times 2 if we say m is equal to 2 outputs, and r we normally say is 3. I should add, by the way, the reason why we've been mentioning 3x3s a lot here is because, as I showed earlier, 3x3s are quite small. The number of parameters is small in comparison to large 11x11s. And additionally, the amount of compute is less. A 1x1 convolution, I might add, is valid, but not really useful if you want to do spatial information. In fact, it's completely useless. But essentially what you do is, this top bit describes the number of tiles. So essentially we said here that we had these little sections of data that we wanted to do this efficient computation over. So we tile up the input, each of these little tiles across an input tensor. There's a certain degree of overlap. There's some arithmetic that goes on. You first do the input transform over all of the tiles of the image. You then do the filter transform over the filter. And in fact, actually, after training, when you've learned the weights of your filter, you don't need to do it further. So you can just have the transform filter. So this can also be done offline in terms of computation. This last little section down here, the penultimate one for eta and nu, I think, you are doing a series of matrix multiplies. So actually, this little dot here is done for an immediate pointwise multiplication. But actually, because of the amount of dimensions that we have in our neural network, we have a variety of input channels, a variety of output channels, and a number of images in our tensor. So as it turns out, we can end up constructing a series of matrix multiplications. So we're still getting the best of both worlds, as we'll see in a second, where you have the efficiency of the matrix multiply routine, but we have now done a provably minimal number of multiplications. So we eliminate the disadvantages of the intercall algorithm. And at the end, you see here how we have m is equal to some indices. We do the inverse transform. We take these transform tiles, which we've now done our pointwise multiplication on. We transform them back. We get the outputs from the direct algorithm. So here is just a random 50 by 50 input that is shown visually in 3D to illustrate this idea of having channels. Let's say, for example, your neural network miraculously learns the parameters in its filter for a Gaussian filter. Not that that would ever happen in reality, but let's say it did. And let's say we picked a 4x4 slice of the filter. So I just picked a random slice from this particular input, and it looks like that. And we'll soon see how these can be combined together and make a nice pointwise multiplication, stacking these up together and then constructing a series of matrix multiplies. So the key reason for why this works is essentially because you can treat convolution equivalently, and mathematics you do this a lot where you say one thing is equal to another, that convolution is equal to the interpolation of two polynomials. If you think back to the idea of FOIL, where you had to take two expressions for ax squared plus bx plus y, and then another polynomial of a similar degree, and you multiply the coefficients of these two together, writing out the expression is equivalent to doing a polynomial multiplication. And it turns out that this can also be done in a similar way with interpolation. This is the Lagrange theorem. This is the basis for the Winograd algorithm. But enough of that. Let's show you the actual bits and bobs. So this essentially is when we've taken an input like this, we've transformed it, and we have 4 intermediate values. We have a filter like this. We see a 4x4 slice of this. And we simply take these and we unfurl them. We do the transformation and we unfurl them as single vectors. So these are the individual elements of the input and the individual elements of the filter. And you see, if you would bother to count, that the number of intermediate values that are computed as the output is exactly 16. So in other words, you take in an input of size 4x4, a filter size 4x4, you compute a 4x4 that's unfurled, you inverse transform it, you get a result of the size 2x2. So what the benefit of this essentially is that if this was with a 3x3 filter, and we do it across a 4x4 slice of input, we are actually, if you would imagine the naive way, we would be doing it with 4 times, because you're convolving it for each of the 4 sections of a 4x4 that you can fit with a 3x3. And essentially this means that we're amortizing the cost of 4 dot products into 16 pointwise multiplications. So if you were to naively do it, you'd see 36 floating point multiplications in the naive case, and in this case you're doing just 16. So the diagonal essentially makes this much more efficient. So what would then be nice is if we said, all right, this is not very significant saving. In compute terms, this is negligible. But I'm now going to try chunking the work back up together again. So in neural networks, we typically have an input of size of some input depth. We said 3 earlier, but often in a deep neural network, the input depth of a tensor can be quite deep. It can be 512, 1024, possibly more. So we want to represent this and essentially stack up the features, the input features, next to each other. They are computed independently after all, so there's no reason why we can't just stack these up together in the same way. And likewise, the depth of the filter, each individual section of the filter equal to the number of input channels is also computed independently from each other. We can end up then making this, instead of 16 floating point multiplications, as 16 dot products. So this is quite nice, and this is a bit better. We have now entered level 1 of BLAS. If any of you know the BLAS levels, level 1 is a dot product. But now we want to try reaching level 3, as that's the one that's been predominantly used and predominantly optimized over the years. So the question now is, can we chunk this work up? And of course, the answer is yes, otherwise I wouldn't bother giving you this talk. But how can we chunk this up further? Well, recall that we had each of these 3 output filters, each of these 3 filters earlier that I showed you, the blue, yellow, and purple one. Each of those can be computed independently of each other. The ordering doesn't matter. You can compute them in whatever way you like. So now, forgive me if that doesn't look so clear, but essentially you take each of these filters, and for each dot product you see here, each of the 16 dot products, you can imagine that you then stack up next to it, immediately next to it, each of the successive output features. And then you have 16 elements. If you count, it's still 16 vectors that you're now outputting, as opposed to just 16 individual elements. And this is better. This now becomes GemV. We now have we now have 16 vectors as an output. So obviously the nice thing to do would be to try and getting yet another dimension added into this equation. And of course the answer is yes. All of this was visualized in 3D Matplotlib. It did take 3 minutes to visualize some of this. I hope you forgive me for using the right library for this. But essentially what we're doing here with adding another dimension is we're adding in the n dimension. Recall earlier that I said that in training we typically want to do 4 images in a batch, 32 images in a batch. So essentially for each vector on the left we batch up with the number of images in a batch. Because again, each image in a batch is computed independently of the rest. There's no reason why you can't just stack them independently next to each other. And so we end up with 16 matrix multiplies. This is exactly where we've arrived now at an efficient algorithm for computing convolutions, and specifically for 3x3 convolutions, which are commonly an optimized target in neural networks. Again, as I mentioned earlier, 3x3s are useful because they are small in parameter count, small in the amount of compute they need to do. So this is quite nice. We've now found out a very efficient way of doing this. One caveat, however, is that we cannot just arbitrarily extend this to larger sizes because of the Lagrange interpolations that I mentioned earlier, the interpolations. Because of the nature of having these interpolations with a fixed number of points, we essentially are trying to predict the shape of a function based on a certain amount of points. It needs to be continuous. There are certain boundaries that must be respected. So it's quite difficult to get actually significantly larger convolutions as a consequence. Although this is an active area of research, I might add. I believe NVIDIA actually managed to get this to work for 5x5 convolutions, I think even 7x7 convolutions. But in any case, this is the predominantly used convolutional layer in neural networks today, and that's exactly what's happened. And recall, obviously, that we had a Gaussian filter earlier. So you can see that the input is now dampened. We see that the results of this convolution, this is the literal output of the computation that we've convolved or technically cross-correlated across the input and produced the correct output in exactly the same fashion as you would for the input. And to give some actual performance numbers on this, I did actually do this on one of SickleDNN's benchmarking machines, which is named Henchmark. I believe we have an AMD Fire Pro GPU running on it. You can see how in the very first layer, where we represent 224 by 224 by 3, so this is an ImageNet sized input, typical image, you'd see that the direct method actually is the fastest one. This is not particularly important because the computation for the first layer is usually negligible relative to the cost of the total network. And you can see that Winograd soundly thrashes it in every single other layer otherwise. Imticol is a commendably fast algorithm and beats it quite handily in some cases, notably the 56 by 56. But you can see how in the middle layer, 112 by 112 by 128, that it suffers quite a bit. If I recall correctly, that is because it starts to run out of memory. You can't fit all of that massively sized matrix inside your local cache, so you have to spill it out to global memory. Slows it down, performance suffers. Winograd is nice, as I stressed, because the amount of computation you need to do is a lot less, and the amount of duplication is significantly less. So from a cache perspective, this is also a very good algorithm to use. You can see how the performance is rubbish in the first one, and actually there's another visual indication of why that might be. If you imagine that a matrix multiply, that there needs to be a certain size of the matrix in order to have enough work essentially to be done efficiently and in parallel, and to cache it efficiently, that the height and width of these matrices need to be suitably large, or large enough I should say, and particularly if they're square, because matrix multiplies are most efficiently computed with square sizes. But if with a 3 by 3 as an input, then, with an input of depth 3, as is the case with an RGB image, the actual width of the input block and the height of the filter block are only of 3. So there's a tiny amount of computation, so the overhead of these transforms, turning it into this and back from this, are comparatively speaking quite high. And likewise, we can actually see towards the end of the network that actually the other problem is the case, that rather than having a suitably large image but very narrow input, that we have a very tiny spatially sized input but very deep input. So with the 14 by 14, there's very few Winograd convolutions that actually need to be done. So in other words, this is not done as efficiently. One final note as another notable implementation detail. From the perspective of neural networks, we typically note that the size of the batch is 4, 8, 16, 32, usually some power of 2, but small, because after a certain point, you start having to do training over the entire data set. And researchers repeatedly find this does not give us good learning. So as a consequence, the height of these submatrices in the input block are typically not very large in comparison to the channels and the output features, which can be hundreds if not thousands in size. So the way we mitigate this, and essentially to pad out the size of these input matrices, is to actually do multiple tiles in parallel. So this is a technique that's known in the paper as superblocking. Essentially, you simply put each of these tiles on top of each other and compute them again in parallel. So you'd be doing multiple output matrices. And the benefit, of course, is that you are putting in more work. The matrices are more balanced in size. Lavin and Gray, if I remember correctly, specifically pad out the size of each of these individual matrices to be exactly 32 by 32. In SickleDNN, we do the much more refreshing way of just throwing all of the tiles of the case and just letting it be solved by the SickleBlast library. But that's just another important point to note. But yeah, the performance of it gradually degrades as the input becomes progressively smaller and smaller, and so the gains, relatively speaking, between the Winograd and the direct method become smaller and smaller and smaller. But nonetheless, it is still a very efficient algorithm. It is implemented without exaggeration in every single neural network library of significance and is widely studied as one of the fastest algorithms for convolutions. So that will be me. Thank you very much.